So in this video, we're going to look at the generation of these diazo compounds. We're going to look at making them from acyl halides and diazomethane, oxidation of hydrozones, or the diazo exchange reaction. So first we have our reaction of acyl halide reacting with diazomethane. So this here is the general formula for our acyl halide. We can vary this R group here to be whatever we want to be, and our X here just represents a halide such as bromine, chlorine, or iodine, basically something that's going to be a good leaving group for us. Our diazomethane is over here, diazomethane, and this exists in a resonance structure where we can move in this lone pair, move a pair of electrons onto the carbon to generate a carbanion. So we have a negative charge on that carbon, positive charge still on this nitrogen in the middle. And this sets up our carbanion, which is going to be our nucleophile in this reaction. So our carbanion is going to come and attack our electropositive center here in the carbonyl. So we've got our delta minus and delta positive there. So that's open to nucleophilic attack. And this here is our nucleophile. So that's going to send up a pair of electrons to the oxygen. That's going to come back down, and it's going to kick off our X as our leaving group. So now we are left with our diazomethane now attached to our carbonyl. So here we're still going to have a positive charge on our nitrogen in the middle here, but now that this carbon has given a pair of electrons to this attack here, now this is neutral. But obviously we need to be able to generate our diazo compound. So we're going to need to lose one of these hydrogens to do so. So we can either do this by adding a base, or we can add excess diazomethane, and the diazomethane will act as a base. So if we add an excess of diazomethane and we convert it into the resonance structure shown here, then we'll have a negative charge on our carbon, and the carbon can take the hydrogen, or our base can take the hydrogen. When it takes the hydrogen, we will give our pair of electrons in this bond to the carbon, and we will reform a diazo compound. So here we formed a diazo compound from a diazo compound, because obviously diazomethane is a diazo compound in itself, but we have managed to add on to the structure of this diazomethane an R group, which is what we want to do. We want to be able to extend the chain length of these of this diazomethane, and that's what we've done here. So we've got a minus on our carbon there, a plus on this nitrogen. And then all we need to do is add in some heat or some UV light, and we can get this nitrogen leaving, this nitrogen gas, and we are left with our carbene, as we showed in the previous video. Our carbene is so. So, like I say, if we add one equivalent of the diazomethane, we'll need to add a base in also. But if we add excess diazomethane, we don't need the base, because the diazomethane can act as a base itself, taking that proton. So if we look at a quick example, we've got an acyl bromide here with a phenyl group attached, and we've got our diazomethane, and we're told we've got two equivalents. So that means we'll be using our diazomethane as a base. So first we need to show the resonance structure of our diazomethane in order to show the formation of our carbanion, which is going to act as our nucleophile in this reaction. So our diazomethane attacks our electrophilic center, moving the electrons up onto the oxygen, back down to form the double bond again, kicking off the bromine. This has now attached our diazomethane to our acyl chloride, It's no longer an acyl chloride now. We've now extended the chain length of our diazo compound. But obviously we don't have a diazo compound yet. We need to have a negative charge on this carbon, and so we need to lose a proton. So to do that, we have another molecule of diazomethane come in. This time I've drawn the resonance structure already in the form that we need. It can act as a base, taking this proton. The electrons in the bond get given to that carbon, and we then form our diazo compound. So we have a negative charge on our carbon, positive charge on this nitrogen in the middle, and a nitrogen on the end there. So you see it's in the same form as the diazomethane, just instead of having two H's attached, we have a H, and we have this extra chain now as well. So we've just changed our diazo compound in order to get a different carbene out if we want to do some different carbene reactions. So now all we need to do is supply some heat or some UV light, make that nitrogen leave, and we end up with our carbene as shown there. So next we have the oxidation of hydrozones. So first we need to make the hydrozone. So we take a ketone and we react it with hydrazine. Hydrazine here is going to be our nucleophile. It's going to attack the electrophilic center, which is our carbon, move the electrons up onto our oxygen. This time we don't have a good leaving group. Like before we had the X, which was a halide. Now we only have R groups. So the electrons are going to stay up on the oxygen in our intermediate. So we form an intermediate now where we have an O minus. We have a nitrogen here with 3 bonds because we had 2 hydrogens already attached. So this nitrogen is going to have a positive charge. And here we have NH2. So you see we've gone from two neutral species to a species that's neutral overall, because we have a minus and a plus cancel out. So now we get a proton transfer occurring where this oxygen steals one of the protons of the nitrogen and the electrons get given back to that nitrogen there. So this is a reversible process. This is a reversible process too. The hydrazine can just leave again, but we're not really bothered about that reaction. We want to go forward to our hydrazone. So we're going to get a proton exchange there where we form a alcohol. We've now got a neutral species again, but we can get another proton exchange occurring where we take a proton from that nitrogen, give the electrons to the nitrogen. Again, a reversible process where we've now got OH2 with a positive charge on that oxygen. We've got our R group still, so all these are R prime, just to show that these can be different groups. We have a nitrogen here now with a negative charge bound to this other nitrogen here. So now we've set up water as a leaving group, and water is a really good leaving group. So what we can do is move this lone pair of electrons in to make a double bond with that nitrogen. So between the carbon and the nitrogen, there'll be a double bond. This carbon can't have 5 bonds, so it's going to kick off one of these like leaving groups, and water is the best leaving group. So the water is going to be kicked off, and we're going to form our hydrazone. So water leaves, and then we form our hydrazone. So this here, we now have a double bond to our nitrogen with an NH2 group attached to that nitrogen. So the nitrogen only has 3 bonds, so it's quite happy to sit as neutral. And this here is our hydrazone. So now all we need to do is oxidize this hydrazone. So we could use something like mercury oxide, just an oxidizing agent. So this is going to be an oxidation to our diazo compound. So this will give us positive charge there, negative charge here. Then obviously we can rearrange this. Say rearrange, we can draw the resonance structure of this, where we have our negative charge on our carbon, positive charge on that nitrogen in the middle there. And then all we have to do is supply some UV light or some heat, make this nitrogen leave, and we are left with our carbene with the lone pair there on the carbon. So the last method that we're going to look at is the diazo exchange. So this is going to be making diazo compounds from 1,3 dicarbonyl systems. So here we have our 1,3 dicarbonyl system. We're going to be reacting that with tosyl azide to form our diazo compound. So tosyl azide, the structure looks like this. So here we have our tosyl part. Here we have our azide. So we have 3 nitrogens bound together directly like this. And this is what we call an azide. So we'll see azides a lot more when we start looking at nitrene chemistry. But for now, we're going to be reacting this with our 1,3 dicarbonyl system to form a diazo compound as shown over here. So if we start with our 1,3 dicarbonyl, as you'll know, the protons in the alpha position are reasonably acidic. So if we treat this with a base, for example, triethylamine, we can take that proton and give the electrons to our carbon there. So obviously there's resonance structures that exist here where we can move our negative charge up onto our oxygens. We're not too bothered about that in this case. So we've got a resonance structure that occurs here where we can move these electrons just like we did with our diazo compound, so that we have our negative charge on this nitrogen, the positive charge on the nitrogen in the middle, still because we have 4 bonds to that one, and that makes this nitrogen here delta positive. So here our dicarbonyl actually acts as our nucleophile, attacking this nitrogen here, which moves the electrons onto this nitrogen in the middle, getting rid of that positive charge. So now I'm trying to get a fresh screen just so we can draw the rest out. So now we've got rid of the negative charge on the carbon here. We have our 3 nitrogens now joined on to this dicarbonyl system. And we still have the negative charge on this nitrogen here. So what can happen is that this hydrogen can give its electrons into this bond here to form a double bond with this nitrogen. As it does so, all of the electrons will move down this nitrogen chain, and in doing so, we'll move this lone pair onto this nitrogen. This nitrogen will leave with the tosyl. As it does so, it will grab that proton. So you see it's all happening in a big cycle system. So this will form our diazo product. With our positive charge and our negative charge, and our leaving group also here. So like we know, this is our diazo compound where we can move our electrons to form a negative charge on the carbon if we want. So this will give us our negative charge here, our positive charge on this nitrogen in the middle still. Now all we need to do is supply that heat or that UV light, make the nitrogen leave, and we get our carbene on our 1,3-dicarbonyl system, like so. So in the next video, we're going to look at how to make our acyl chlorides or acyl halides in general, just so we can make them if we're ever asked. And then we can build up then obviously to our diazo compounds, then build to our carbenes. And then after that, we'll look at the reactions of these carbenes.